Good. Okay, so everyone, so thank you for attending this week Progressing Efficiency Seminar talk. And today we have Dr. Cheng from the Microsoft Research to give a talk with the title Transformer Efficiency from Model Compression to Train Acceleration. And Dr. Yu is principal research at Microsoft Research. Before that, he was a research staff member at IBM Research. He got a PhD degree from the Northwestern University in 2015 and a bachelor degree from the Tsinghua University in 2010. His research focus covers deep learning in general with specific interest in model compression efficiency, deep generative model, and adversarial learning. And currently he is focused on production these techniques to solve challenging industry problems in computer vision, NLP, and multimodal learning. So now let's welcome Dr. Cheng to give us this talk.
Okay. Thanks, Paul, for the introduction. So yeah, I'm very honored to be here today to present the work, Transformer Efficiency. And today's talk about green energy and energy efficiency and model efficiency. So we all know that transformer models have been achieved a lot of success in recent years. For example, in natural language processing, BERT, trained on a means of corpus, NLP corpus data like Wikipedia, have dominated the NLP area for many like natural language understanding tasks. Also recently, we noticed that some models like GPT-2 and GPT-3 also trained on many of like news data and large corpus show a very like human-like the generation performance on different benchmark. Beyond that, like we saw from last year to this year is also something called a vision transformer, which just applies the same or almost the same architecture to the vision problems. And we all know that this VIT model, vision transformer, already achieved the same, maybe a slightly better performance than traditional CNN. So both of them have shown that the transformer models or the so-called self-attention mechanism have been very successful in both NLP and computer vision. A problem for the transformer models, or not just transformer models, but all the other general deep learning models, like the model is keep growing. We saw that BERT have like maybe like a few billions of parameters, but then we saw some model like a robot at GPT-2, T5, like a turning LG, or like the GPT-3, even have like around 200 billions of parameters. So we say that as the parameter keep growing, the model size and training and inference time are critical when we try to apply this kind of models to different products or applications, especially for some application platform like Microsoft, because Microsoft serve a lot of like not just 1P customer, but 3P customers or the third-party customers, which have very limited computational resource. So that's why we have the motivate to say, how can we achieve a efficient model, then still keep a good performance? So one way or very straightforward way is we can do model compression, right? To compress the transformer models to some smaller size, and also we want to keep the almost the same performance. We have started this problem like maybe 2 years ago from 2019 after BERT appeared. So the first things we're starting about model compression noise distillation, right, is a very straightforward way to do to compress models. And we have tried something like a patient noise distillation and a construct distillation. sometimes we also think about something like a traditional pruning, right? And like we did for traditional CNN. So we did something for pruning for BERT, Robota, but also recently we have tried something to prune the visual transformer. Then after that, we think about the model compression only improve the inference efficiency, but how about the training efficiency? Because training such large kind of models, even just one time part, but it still take a lot of time, especially on some customer data. You need some model to fine tune. You need some data step to fine tune your model. Then it's still very time consuming. So we try to think if we can use similar techniques to improve the training efficiency. That comes our very recent work on early BERT, it's called efficient BERT training with local tickets, and also another work to called class former to handle long sequence. For today's talk, I will not cover all the whole works I mentioned here. I only pick some of them and to give you some examples of how we do the transformer efficiency in Microsoft. Here's some topic today. So for knowledge distillation, we're talking about like patient knowledge distillation, and also how to use contrastive learning in knowledge distillations. And for pruning, we were mainly discussed how to using pruning techniques to training acceleration, and also how to do something called dynamic pruning to save both the memory cost and also the training or the pruning cost. Also, you will say something like even it's all the same architecture for both NLP and vision, but still because it's vision and NLP problems, there's still some difference between them when you compress a vision model, vision transform model or NLP transform models. So for each part, I will have some stop after each sections, and feel free to ask me questions after each sections. Okay, let's start here. So the first topic we are talking about knowledge distillations. Before that, I will give a brief introduction or some recap about the transfer models. So different from MLP and CNN, the transfer models have some we call different architecture. So I think the first things you need to remember is this one called the multi-head attention. It's just taking the input embedding, either a sentence as a sequence of sentence or a sequence of image patch, plus its positional encoding, which means for NLP, it's just the position of each words. And in communication, for image, it's just the position of image patch. Take both the token embedding we call, and also the position embedding, and do some mechanisms we call the self-attention. And then after the self-attention, you can do the one head attention, which just have attention mechanism between these two inputs. And but for one sentence or one image, you can do many attention. So actually, you get something called a multi-attention head. It's not just the one attention head, but multiple attention head. This is one very important component. And also another one, after several steps of multi-attention, you can have an MLP layer called feed-forward layer here to aggregate all this multi-head attention for the next level informations. So when we call unstructured pruning, it's the same as we did for CNN or NLP, just prune the neurons. And for something called structural pruning, which is different from CNN to prune the channels. Structural pruning here means we will prune the size of these MLP layers, and also the the attention head, because we have multiple attention heads, not all the attention heads are important or useful. So some are redundant. So when we say call structural pruning, it's just to prune this attention head and MLP layer. And some structure of the model we'll talk about today, like BERT or GBT, it's just aggregates the different transform layer back and to form a very deep transformer models. And it will do something called the pre-training or fine-tuning to get the final models. That's how BERT and the GPT 2 or 3 works. Also, some like a training paradigms for language models. This is not true for computer vision, but it's true for language. So in language, we know that something like BERT will have some step called pre-training. We will say here called a semi-supervised pre-training. It's just to use this randomly initialized BERT models, like I mentioned in last slides, to train on the unsupervised corpus, which just you only have the corpus self, and you will do something like MLM, master language modeling, or some object you call the next sentence prediction, and you'll do some like self-learning, something called semi-supervised learning, or called the pre-training. Is all same. And after this pre-training or self-learning step, you will get some trained BERT, and you will move to the next stage called the fine-tuning step. It's supervised the fine-tuning step, which means you have your own task and your own data set, and you will use that label and the data to fine-tune the weight of the pre-trained BERT. So remember, for all the current NLP applications involved large BERT models or GPT models, you will always have these two steps. One is pre-training and one is fine-tuning. So any questions so far? Okay, good. Okay, let's talk about the compression or KD part. So as I mentioned, for BERT, you have multiple layers. Like we have BERT large, which have like a 24 layers transformer, and BERT base have like 12 transformer layers. So the very straightforward to compress mode is like you can compress the layer part, right? Just do like traditional KD. For example, you can get some like a 6-layer parameter, a 6-layer BERT, which only have like a 67 mini parameters, and also even you can get some 3-layer transformers, only have a few parameters. You will say that it's not linear declaration for the parameters, because we all know that for some BERT, some model like BERT, it's not only the layer take the parameters, but you also have the input part, right? As I mentioned, you have the token input and also the position input. That part also takes some parameters. So it's not a linear declaration as a layer decorates. So I will just mention this for your notice. And after this compress step, you will definitely get something for benefit, right? And usually work 2 to 4 times faster for the inference. As I mentioned, it's not a linear declaration as a layer, and you'll get more something 2 to 3 times memory efficiency after you do KD. So what's the logicalization we find for something like BERT compared with like traditional knowledge distillation? So for this one, you still have the text-related loss. It's just this is for fine-tuning of pre-training. Like for pre-training, you will have something called, like I mentioned, the MLM loss or next sentence prediction loss. That's like we call the text-specific loss. And also, if you have your fine-tuning step, you also have the your data and the label. You can have the loss, right? And the last loss is we will try, like a traditional KD, we will try to mimic the behavior of the teacher model and the student model, which just match the KL divergence of the output layer. That is traditional. But we found that for something like a BERT, because it have the transformer layer and also it's aggregate different a lot of transformer layer together. So it has the intermediate layer, which is also important to take into the KD performance, the KD process, which means when you mimic the behavior of the teacher model and student model, you not only mimic minimize the output of the last two layers, but you also want to match the behavior of the intermediate layer. That's even called the patient, because it's not just the mimic the last layer, but also the intermediate layer. You will have the student, the patient learn the teacher behavior instead of just match the last. So the final loss have three parts. One task specific loss, and then KD loss, and then we call the patient teacher loss, which match just the L2 normal between the two intermediate transform layer. And because we have this PT loss, so there's two ways to construct this PT loss. One is called the PT scap or PKD scap, which you will have the layer to jump to next and to match them together. Like we have here, you have the last layer to map, and you also have like if this 12 layer, right, you will match to another 12 layer, that's fine. But this is for like the 10th layer and match to this 5. Just you skip one layer to match, because your teacher model will have less layer than your student model have less layer than teacher model. So we'll skip some layer to do the matching. And this will call the PKD skip. Also have another version called PKD last. It's just directly match the last few layers to between the teacher and the students. Like this is the 12 layer BERT and the 6 layer BERT. So you will match from the 7 to 12 and to the student model from 1 to 6. So we don't have some survey to compare which one is better, but empirically we found the PKD skip is slightly better than PKD last. Okay, let's show some power of this patient loss. First, we check if we directly do just the traditional logic distillation. You will find for different datasets. This is all dataset on the GLUE benchmark, which is the largest one, the natural language person understanding. You will find that there's some gap between this is a training, and you will find there's still some gap between the original BERT, which is the baseline, and also the not descaled BERT. If you want to descale from 12 layer to 6 layer. And how about the patient loss? On some data sets, that we saw that it's almost the same as the baseline models, which is the 12 layer models. On some data sets, it's still worse, but obviously it's all out from the traditional KD. So we say this patient's KD is better than traditional KD. That we got that's what we learn from this like BERT distilled processing. And also have some final results showing on different data sets. As you say, we use the BERT-based models, which is not from Google. We train ourselves BERT-based. This is slightly better than Google BERT models. And we have distilled 6 layers and 3 layers models. And you can see that for the 6 layers, the performance maybe like around like 0.5 or 0.7 degradation than the baseline. And for the 30-layer model, it's much worse, but it's still acceptable because all these numbers are good than much better than the traditional CN or iron models in LP. So it's still acceptable if you really deploy it on the product. Okay, that's the PKD. And we have the transition from PKD to CODIR. So we learned from the PKD paper is that the individual distillation also important for the KD, right? Which means this loss, the PD loss, is something important to count in the whole loss or the KD processing. So we will think about here we use L2 norm to calculate just directly match the distance between two intermediate layer. It's a good measure for this to hidden states or called hidden layer. The answer is no, because we know that L2 norm is cannot capture the very rich information or internal rich information between two transformer layer or transformer hidden layer, right? So what's the solution is we'll try something different instead of just use L2. We use something called the contractual loss, which is I think everyone heard that it's a very famous term in recently self-learning or self-supervised learning. And we compiled different methods using regarding using the intermediate layer distilled. Actually, you can say for PKD, both PKD and the TinyBERT, which is also very good work for knowledge distillation. And both of them use this like L2 norm loss for the intermediate layer. And our work, like we argue that we can use the contractive loss for the intermediate layer distillation. And also some other difference. And then another part our CODIR work want to is because PKD only do the fine-tuning step. As I mentioned, we only have the Pretrain-BERT to do the fine-tuning, but we haven't to try the pre-training. So the CODIR work we also try pre-training. That's the 2 points we got from CODIR. And for the contractive loss, this is the whole framework for CODIR work. I think it's not much difference. Just one things we need to mention. I need to mention is like we use the. This is a very traditional contractual loss, just N4 in the E loss, right? You have contract by a bunch of like positive samples and you have negative samples, and you're using the inference E to match the loss between two transformer layers. That's how we calculate the contractual loss. But this one issues to using contractual loss here instead of directly use L2 norm loss here is like because you want to calculate this info NCE contractual loss, and then you need to both construct a bunch of positive samples and also negative samples, right? We all know like positive samples is simple, just you can use in batch samples, in batch positive as the samples, but for negative it's different, right? Besides the within batch negative positive, all the others should be counted as like as negative. So how can we like sampling such a kind of large of negatives from very large corpus, especially if we do fine tuning is okay, but if we want to do pre-training, the number of data for pre-training is very large. How can we sampling a very large of like negative samples to calculate the N4 NCE loss? That's one issue. So strategy we use here is like we will use something called a memory bank for each epoch or for each batch to store some positive data from the batch, and we call it memory bank. Just store all the positive data. And negatives, we try different method, but finally we come up with like in-batch negative samples, because we try to calculate more or sample more from large batch, but we found it's very time consuming. So finally, we just use like in-batch negative, which just accept the data in the memory bank, the positive memory bank. All other data can be assembled as negative samples to calculate the N4 instantly. Here's the result of CODIR. So you can say first we have very strong baseline. This baseline just you train a BERT-based model like here. Actually, we use a robot as a teacher. So you will say our baseline is you use 12 layers robot, and you just truncate the last 6 layer, and you'll get some performance. So you will say this baseline we want to compete is very strong. It's even I think it is better than most of the state of knowledge distilled models. Like it's only slightly worse than the TinyBERT 6 layer, but the baseline is very strong with only 6 layer robot. And a second message, like when we use this pre-trained weights to fine tune and do CODIR distillate on to another 6 layer version, we will say that it's better, it's much better than the baseline. Also, it's outperforms state of ours, which is the TinyBERT 1, than by 0.4. Okay. And the third thing we mentioned that how to compare the fine tune, because for the CODIR we do both fine tune and pre-training. So we'll say if you directly do pre-training on the for the distillations, you will get better performance than you only do fine tuning, which means if you distill models on the pre-training stage, it's work better than you do on your fine tuning. The reason is like the pre-training will have more information, and it's somehow called a task organistic side. So it's have a better gain. So we'll say that instead of outperform star rate by 0.4, it's outperforms the sorter by 0.6. And also you were curious about how to combine them together, right? So that's other way did for pre-training and fine tuning together. So you will do distill your models on pre-training stage, and you will do same thing for fine tuning. And we found that it's actually it will not give you much of the gain here. Like it's only, I guess it's something comparable with the only pre-trained model. So the conclusion that actually you can only do CODIR pre-training. It's already enough to get the best performance. You don't need to do pre-training, CODIR pre-training plus CODIR fine tuning. And this is some ablation study, like both show that either fine tuning or pre-training or the contractive loss help for different baseline. I will have some discussion here for distillation, then we'll have some time for QA. So first, I want to mention that although we found that for both work, the teacher model is important, right? So we all know that the teacher model, the power teacher model, probably the better distilled or compressed model you can get, a student model you can get. But actually recently we found that this is not true. So sometimes you can use not that good performance the teacher model, you can still get pretty good performance. And we are investing what problems like for my understanding, like the KD loss is something like a regulation. So which means you can only use something different instead of something very powerful, you can get the same performance. Another one, as mentioned, like we are still investing how we can get more sophisticated sampling instead of that in batch negative samples for the pre-training to improve the performance of CODIR, because we need to think about both the pruning efficiency and also the final performance. And also some experience from how to deploy this model to Microsoft products. We found that usually it's come to this two principles. One is whatever product or model you want to deploy, you will definitely get some performance degradation. Especially, I think for some products, we cannot even use like a 6-layer BERT. We have to use like 3-layer BERT to satisfy the computational efficiency. So in that part, you will see a very clear performance degradation. So we will use different data augmentation tricks or other training tricks to mimic the performance degradation. That's the one. And also because it's for different fine-tune tasks and different data. So how to find a very proper temperature for the KD loss is very important. It's also for some other hyperparameters. Yeah, that's the conclusion for the KD part. And yeah, I will give some time for the question. Any question?
You can hear me?
Yes, go ahead.
Thanks for the great presentation so far. So I have a quick question about the patient knowledge transfer after distillation. How is that affecting the accuracy-wise results you showed, but how does that affect the length of each epoch or the number of epochs required for training, given the much larger number of parameters that you need to kind of match between the teacher and student models?
Oh, you mean that will affect the pruning time, right?
Correct.
Yeah, so that is our there were like affect the fine-tuning both pre-training and fine-tuning time, especially for pre-training, because we saw that this for fine-tuning it's fine. I think the difference is not that much, because fine-tuning you will get a very smaller data, and when you're adding another loss to the final loss, it will not affect much. But for training, yeah, definitely there like 20 around like 20 per it will take 20 around 20% more time to finish the training. But because for I think for the pre-training, especially if we want to do some task agnostic one, it's just one time. So yeah, so that's also acceptable.
Absolutely. I'm actually, it's very kind of impressive, like with that many more number of parameters that need to be matched, only 20% more time in training. I mean, is that?
It's 20 to 30, yeah, if I remember the whole time.
Thank you very much. Yep.
Yeah, because another things you want, like because you're adding this patient distill loss, it's not only improve the final performance, but it's also improve the your conversion rates, which means for fine-tuning, though, you will not do the if you only have KD like for glue, you have to do 3 epochs or 4 epochs to achieve the converge. But if you're adding this a PT loss, it definitely you will finish in 3 epochs. So for the epochs part or training step part, you also save a lot of time. Yeah.
Very interesting. Thank you.
No problem. Okay. Okay, let's go to the next one. Okay, so next one called early birds. Inform BERT training for early BERT local tickets. So the motivation cause or inspiration from lossy from the local ticket hypothesis, right? Which you can have a unstructured sparsity giving any network from a theory. So the way you can get this mask or this sparsity mask, you can do something called IMP, iterative magnitude pruning. But we all know that actually unstructured pruning, given the current Haval environment, you will not get any like efficient side for both inference and training, right? Because this unstructured part cannot speed up your model, given the Haval. And we are noticing another work called early BERT tickets, which published in iClear 2020, which have some structured pruning, which is a channel, and you can get a better supportable accelerations. And also the early BERT tickets paper told that you can find the tickets not after all you do the MP, but you can find the tickets actually in the early stage of the full model training. Also, this gives some hints to how can we save the training, how can we save the training time. So this work we target the training efficiency, which means the first we will use structural pruning instead of the unstructured pruning near local tickets to find something called tickets in the BERT part. And also we will say, because you already have this like you will already find some tickets, right, which is sparse network, have less parameters. But when you train either fine-tuning or pre-training, you still have the same number of data to train. And we'll think about how once we have this pruned network, can we train this network in some short time than the original training? Because original training is you from very not compressed models, but here the after you find tickets, you will train from the compressed or compact models, and we'll check if we can save more time. This is some hypothesis. We don't have any theoretical guarantee for that, but it's all from empirical. So okay, as I mentioned, we only do structure pruning for these transfer models, which prune the attention head and also the MAP layers. So the method we use for the structure pruning called legwork slimming. I guess many people will know that work for CNNs. So it's just adding a coefficient, a coefficient is a parameter for each component or each part, and you will use N1 norm to calculate the coefficient. And after that, you will prune each part or each structure or components, giving the number of the coefficient. Means smaller per coefficient, the higher chance will get pruned. And as we know that from the early BERT papers, you will get your tickets not until the full training. You will get at the first stage of the of your training. So we will try that. How about we can try this 0.2 epochs? Can we get this sparse structured network? So we're using like a less epoch to get the tickets. And after that, because as I mentioned, you get some compact models, and but you still train with the same amount of more data. So we will try to say if we just increase the learning rate a little bit, both the fine-tuning learning rate and also the Pretrain learning rate a little bit, and we can also shorten the training epochs. Like we try from because usually it's just 3 to 4 epochs for the fine-tuning. So also try 2 to 3 epochs for the fine-tuning, giving this compressed network. So this is the conclusion, but I will give more the results later. So here is the work of the contribution work. Because we first try, it's all something called hypothesis, but already tried out on BERT is used. So the first contribution is we found for some like transformer models, you can still use less epoch to get some ticket mask. And then we found that using this ticket mask tickets, you can shorten your training epoch, your training step, giving the same amount of more data. So overall, you have the efficiency from 2 parts. One is from the structural pruning, which naturally shorten or improve the efficiency. Another is definitely you shorten the training epoch or step that will give you more efficiency. So efficiency part giving to from 2 aspects, and this will generally give you like 30 around 40 time saving for training. And this is some discussion or things I would skip here. So let's go back to directly to the results. So first we'll ask what's the difference of you do this structural pruning compared with the random pruning. The answer is this find it or train the structured tickets is better than random tickets, right? As we see here, if you do, this is a result from early BERT's base compared with the random pruning, the same compressed rates or pruning rates. Definitely it's better, more than 1 point better than random weights, random tickets. And also we found that in the early stage, you can definitely find something meaningful instead of until final training. So it's time involving for you find the tickets. You can say during the first 0.5, it's already find some tickets. I will split all the parts and go to the final stage. So we do this for fine tuning mainly, but also some pre-training. But pre-training is a little bit tricky, I will mention. So for fine tuning, we try on different glue benchmark, this 4, and also the score data set. And you will find that for this is BERT base and also BERT large. For both, we can the early BERT base of BERT large can save like 35 to 40 or 40 to 45 training time, while almost maintain the same, slightly worse. I say the gap is among 0.5, but it's will save half of the almost half of the training time. Also, we try this a little bit for pre-training, because pre-training for BERT is a little bit tricky. It's have 2 stages. One stage you train your model on some short sequence, and another stage you will starting train model some longer sequence. So we need to speed the 2 parts and do some step for each split. We will do the same thing as before, but usually we try a different like glue data set and also SCAT. You will say it's also save like 35 to 40 training time, but also have some like performance degradation. It's around 0.8 overall. Okay, here it's like some feature work. I will skip because it should be the final work. So here we also continue after the PKD and also pruning and also the early birth. We have some like thoughts on the current transformer model compression. The first I think is very mentioned. I just mentioned because we will find like for transformer it seems a little bit harder to compress than CNN, because we know for CNN you can get for unstructured you can easily get like a 90% compression rate while maintaining the same performance. But for transformer, this threshold is around like 40 to 50. After that, no matter what kind of method you are using, you still get some performance degradation. So we're starting, is it caused by data or some internal mechanism for self-tension? That is something we was thinking. So finally, I guess I will give a few minutes for the recent work we did for the vision transformer exploration. So let's back from the NLP side to the vision side. As I mentioned, the VIT uses the same architecture of the transformer in NLP. So the only thing different is like here, instead of feeding the word, you're feeding the image patch. And also because this image patch order is a little bit, or the position is a little bit different than the word. So therefore, but I also feed the image patch and also the word embedding. And what's the difference here? So for this VIT pruning, we also think we need to improve the training or pruning efficiency. And also because it's image, right? So usually you will say there's some redundancy giving the image data, right? Because if we want to classify this image as a building, actually something in the background is not involved building can be pruned. So instead of do only model compression for NLP, because for NLP, the data is just the word, right? It's not trivial to just prune any word. But for the image data, you can also do the prune on the image batch. So we do both the model and the data pruning. Data means the token. The method we use to save the pruning or training phase is called the dynamic sparse training, something dynamic exploration. So I think I guess some people in this talk will know what that is. It's a very like a new or normal method recently proposed for comparison. So the idea is instead of you prune for a large network, you can start from already sparse network. For example, we want to target the 60% pruning. We'll start from some 40% compressed network. But for each time you just find the neuron, first you will do you will do groaning to grow some number of neurons you think is important based on the gradient of the loss, and then next step you will do something called pruning. It's just after you do groaning, you will find some neurons with you will find the magnitude of each neurons, and based on that you will just delete or drop these neurons were very small number of magnitudes. That's how the dynamic step. And we found that because you're starting from some efficient the compressed model for this dynamic explorations. First, you will save the memory, right? And secondly, because you do all the calculations giving a compressed network. At the same time, you will save some time for the pruning or training. That's why we thought this is maybe benefit for the training or pruning efficiency. And we did everything, structure, unstructured, and also, as I mentioned, is the token side pruning. There's some like step. And we find like for VIT, for the structure part, or both structure and non-structure, you can do at most like 40 to 50% pruning rate, and you will maintain the same performance like for VIT base, for VIT small, and for VIT tiny. For VIT tiny is tricky because this model is already very small, so it's only get like 30% capacity while maintain the same performance. But for other two, it's better. And here show some like a visualization for different attention head. You can say for structural one, definitely you will get different attention head pruned for different layer. Also, here's some examples of how we do both the data or the model pruning. And actually, you can do like 10 to 20. You can prune 10 to 20 of data tokens, while you can also prune like 40 or 50 for unstructured and structured part to maintain the performance. And you will see some visualization for different images to get the token pruned. Okay, I think I finished all the talk. Thank you so much. And we still have a few minutes, right? And if you have questions, you can ask.
Hi, thank you, Yu, and very good talk. So, any questions from the audience?
I have two questions.
Mm-hmm.
The first one is when you prune the vision transformer.
Okay.
So you compare with the data equation transformer. So I know that the data equation transformer is based on only ImageNet training data set. But how about your pruned model?
You mean the experiments is on which data set, right?
Yeah.
It's only on ImageNet.
Okay, so but the architecture, I mean the architecture of data equation transformer is also different from vision transformer. It adds the token, the distillation token to the model. So how about your model?
Okay, so I think we're starting from this VIT or called BERT, if you heard, because there's two versions for VIT. One is the very previous version from Google. Another is the improved one for Facebook. I think they both use the same architecture, but just different training settings like learning rates or some scheduling. I think we only work on the DIT, and for DIT you can say tiny, small base, and all the inferred version or the pruned version is based on the DIT versions. So I think the architecture is the same.
Okay.
I don't know what do you mean by as the
yeah. I mean in the data equation transformer, it has another token, which is distillation token, and they train the model using a CNN teacher model.
Oh, I see. So
Yeah.
you said how about adding distillation? Because this paper only talk about pruning, so we were not adding like a distillation part, because distillation actually you involve more information than the one used here, right? Like if you use some larger teachers, probably it's okay better. But here we haven't used any like logic distillation techniques. Yeah.
Okay, but your performance is still better than the date.
I think it's comparable. On something like base, we find some surprise like like this one. We don't know what happened, but actually DA base only gave you this is some number we get from the paper. And but definitely we get something better than the DA base. But for other two, I guess it's slightly worse or comparable.
Okay, thank you. So the second question is, I noticed that many compression methods have already been well explored in CV field. So so straightforwardly, so we can directly transfer this pruning, this compression method to transformer, even NLP or CV transformer. So what do you think we should take care? What point we should take care if we use the already explored compression technique to transformer compression?
Okay. Yeah, actually, this is a very good question, and this is something we are looking for right now. So I think the talk I mentioned today, most of the techniques are actually from the CNN part, right? Or you can say all the part are from the CNN pruning, either pruning or noise stealing. But you can still find something different, like the PKD loss scale, right? I don't know any CNN work involved that using this PT loss before, but I actually find that's useful. And also because the architecture of the transformer is different for CNN, so you'll find that when you do something like a structural pruning, actually it's different than you prune the channel in CNN. So actually you prune the attention head and also the MMP layer. And we all know that prune CNN convolution kernel is easier than prune MLP. But here you prune the things you want to is MLP, right? And also this this attention head. So these two are very, I mean, it's very difficult to prune, or it's very sensitive. So yeah, take out of that if you want to use the same techniques or hyperparameters for CNN here. And another questions I also mentioned, like we found that for the transform pruning, it's actually difficult because we can easily get like a 90% pruning rates or even 95% rate for CNN while maintaining performance. But the transform pruning, you can only get 50% or even 60%, and the performance get drop. We found that or we have some studies showing this might be led by this self-attention mechanism, which is different for CNN. Like for CNN, once you prune the match of the neurons, the other neurons or the remaining neurons were still useful or maybe more active than usual. But because it's like the self-attention part, once you prune a lot of neurons in transformers, the neuron is not just it's becoming inactive. That's something we're finding. So I think that the short answer is because this self-attention mechanisms or self-attention operations, so it's different from the saying, yeah, the neuron, the dependence of the neuron become weaker in transformer.
Okay, thank you.
Okay.
Other questions from the audience?
Hi, Chen.
Hello.
I have one question.
Mm-hmm.
You've mentioned in the SVITE works that about the pruning and growing and grow, right? In the last slide.
Mm-hmm.
In the next slide, yeah. So is there any the pruning? Is there any proof that the pruning and grow, it will work because for me, it seems like a similar to a random search from a sparse distribution, right?
Okay, back to this DST, dynamic sparse training. Actually, it's not first used by VIT. It's used in CN, and the very recent one is REG-L, I guess. So the idea is not just random. The first part, if you only say the job, right? The job part is exactly the same as we did for magnitude pruning, which you find all the weights, but find those weights with very small numbers, just prune them. And the growing part is also have signals. You not just randomly select some neuron to grow, but you will find you will calculate all the remaining neurons to find those which will have giving the loss and the gradients will have more gradient to grow to get this neuron back. So it's not totally random. Yeah, and yeah, as I mentioned, this method is not. It's not first used by VIT, I must admit. But the idea of this DST is that instead of you can have the full network to prune to a small one, actually you can get a prune or you can get a sparse network as an initial and to dynamic adjust its weights and neurons.
Sure, thank you. It has been proved that it can be a very efficient strategy in other works, right? Sure, thank you.
Other questions from the audience? So if no more questions, so actually I would like to ask two questions. Yeah. So one is just on this slide. So yes, so we know that the REG-L that is first used for the sparse training for the convolution neural work. Mm-hmm. I was wondering, so in your work, so what is the main purpose of to utilize the sparse training? To try to accelerating the training speed, or try to just to get a more compact model from scratch? Because according to the REG-L, the original paper, so if you want to achieve the same accuracy, so actually they need to actually sacrifice the training speed. The theoretical flops will be even higher than than the dense model. So I remember in that paper. And if you want to actually get the more compact model, so for the training speed, so in that case, so actually you need to have the huge sacrifice on the accuracy. So I was wondering, so in the industry, so what is the main purpose of to exploring?
Okay, so
this type of
okay, let me let me make sure it's all right. Okay, the first why we choose DST, there's two motivations. The first is we are targeting some sparity around the 20 to 80, which is reasonable for transformer, right? Because transformer cannot get a very low or very high per compression rates. And I'm not. I guess it's true that DST is the best one among this middle range. I call it middle range compression rates, right? And but because for higher capacity, you will say like local tickets is the best, but for some medium compression rate or sparsity, I guess DST is the best, or REG-L is the best. So, and we also try other pruning method like IMP or MP to show this is true for even for a VIT. But I haven't put the result here. It's in Ablation Study. And the first motivation is the performance side. Another motivation is I don't know. I guess it's the units or the operation side flops or computational cost DST is less than the training the full model, right? Or other part, I don't know. But we are doing here is mainly for memory efficiency, because you still maintain some sparse models. Like when we transfer this, like we will ship this model to some products, you will have a very low like memory cost, and where you do fine tune or you do something training. So it's will save the memory. So the memory cost is our main concern compared with the time, the training time cost or pruning time cost.
Okay.
But I can tell you the results is like we found a train. This DST prune is the time cost is slightly lower than training a full model. This is something we are very acceptable because we reduce the memory and you train the sparse model is using the same amount of time than you train a full model. This is very acceptable for us. Yeah.
Yeah. I remember the similar phenomena observed in the regale. So they can achieve like using the 87% of the flops. And
Yeah. We found that similar. Yeah.
Yeah, but for me, I think that is not not very significant because I expect more.
Yeah. But for us, the main concern is the memory side, because actually some customers don't have that memory to host the model. They need some, the computer resource is low for giving the memory.
Okay, here you mentioned memory, so that is mainly for the target for the edge end or for the cloud?
Edge.
Okay.
Yeah. For cloud, I guess we don't have any constraint.
Okay.
It's very powerful.
Yeah. And my second question is about this more about general. So we know that recently, so there's many exciting progress in like the vision transformer and even for the MLP in the CV. So from the perspective of the industrial researcher, so how do you think about those the current very hot trends that to some new architectures to try to replace or partially replace the CNN and how about the industry's intention?
Okay.
From the perspective of the practical scenarios, what is the pros and cons for the different architectures in practice?
Okay, it's very broad questions. So at first I will ask, I answer for the MLP side, right? I think no matter MLP or other architectures, so I guess BERT, something like BERT or BERT-like or GPT-like model is still dominant. And that's for the MLP. And for the vision, I guess it is a clear trend that the MLP and also the transform models are both very promising. And I guess people are still doing their work to chasing. But I can tell you something, and it's not news, so it's not secret. Microsoft already replaced the original CNN models, something like efficient net or we use for both image recognition and like something object detection model to the transformer models, which is showing the success of transformer model. I don't know whether we will replace that with something called MLP, but I guess the transformer models giving some hints like this, something called self-attention stuff is very important. But not all the things are related to self-attention is important. And you can say some step in the self-attention operation can be job. So that's something people are trying to have different work to improve the efficiency. But I guess self-attention itself, this idea is useful. And I don't know for MLP, but I guess for the vision side, all the three kinds of models, finally, I guess they will get some very similar performance. given different models. So in that size, I guess people will compare with another dimension, like which model is more data efficiency, or which model is easier to adopt to some size, to some environment with lower computer resource, which means easier to be compressed. That's some opportunity. Like I think people here we are all kind of working on that side. But for me, I do not have any preference, right? Okay.
Thank you.
That's my answer. It's very broad questions. I can answer in that way.
Thank you. And any other questions from the audience? Okay, so then we will end today's talk. So again, thank you, Yu, for your very exciting and wonderful talk. And also thank you all the audience to spend your time to attend today's seminar, and see you next week. Okay.
Thank you. Thank you,
Bye.
Bobby. Bye.